Good afternoon, everyone, and welcome to day 3 of Engineering.com's inaugural Digital Transformation Week. On our first day, we covered how to manage data and how to get value from it. Yesterday, we spoke about how to scale up a digital project from the pilot phase, and today we're going to take a look specifically at AI and how to make it fit into your digital transformation strategy. I'm Michael Willett, Senior Editor at Engineering.com, and I'm really glad you decided to join us today. Before we get started, I need to go over some housekeeping. You can download the slides and any additional resources for today's presentation in the resource window on your screen. Please submit any questions for today's experts in the Q&A window. If we don't get to your question, our presenters can reach out to you afterwards. And finally, if you're watching this on demand, you can still use all of these features, including sending questions to our presenters, and we will get them answered for you. So let's get started with today's webinar. I'd like to thank SimScale for sponsoring us today. And today's webinar covers how to scale AI in engineering. It's a practical blueprint for companies of every size. Engineering leaders everywhere are experimenting with AI pilots, but many remain uncertain about how to move from experimenting to production scale adoption. The challenge is not primarily about what algorithms or tools to select, but it's about creating the right blueprint, where to start, how to integrate with existing workflows, and how to scale in a way that engineers trust and the business can see immediate value. Today, we're joined by David Heaney, co-founder and CEO at SimScale, and Ian Pegler, developer relations for computer-aided engineering at NVIDIA. Unfortunately, Martin Meingasner, the development engineer at Hirschvogel eSolutions, has been pulled away at the last minute, and he is unable to join us. But these gentlemen will do their best to fill in and help us explore how companies are combining foundation models, predictive physics AI, agentic workflow automation, and open infrastructure into a strategy that works for small teams seeking efficiency gains, all the way to global enterprises aiming to digitally transform at scale. David, there's a lot to break down here. What's the starting point? Where are some places that AI fits naturally into a workflow?
Thanks a lot for the introduction. That was a mouthful there, the handover here, like a lot of buzzwords to unpack, but hopefully over the next hour or so, Ian and me can unpack this a bit, unfortunately without Martin today. But I guess maybe to send a few words before, thanks everybody for joining. What we try to, or what we hope to achieve over the next 50 minutes is not a solution to everything, not look, we have the answers to everything, but hopefully like a couple of really practical starting points of where to start. We're going to show a bit of something in action. We're going to make specifically the second half of the presentation very hands-on. So we're going to show some real AI in engineering workflows in action, and hope to, with that, ideally maybe show you a starting point, or at the very least give you clear inspiration how other engineering teams start that. And I wanted to sort of start off with a small meme here, because we talk with engineering leaders at this point, with several daily about their AI adoption in engineering, because the starting point is oftentimes the same, because everybody in knowledge work, everybody in engineering has now seen a large frontier AI model do hours of knowledge work in seconds. And so everybody has seen how the productivity gains of a good AI implementation can look like. But everybody asks the same along the lines of, why can I use this for code generation? Why can I use it for image generation? Why can I use it for all sorts of interesting knowledge work, but not for core engineering workflows? And at this point, we have a bunch of memes to show, like AI is fantastic at many things, like the large frontier AI models, but why are they not capable to do core engineering work? And we're going to unpack this a bit today on why that is, and how there's still a proper path to use AI in a productive way in engineering workflows. And so over the next 50 minutes, we're going to show a few examples on how. And that's, I guess, roughly the agenda. With the only, so we're gonna just like start 10 minutes before I hand over to Ian and see the perspective from NVIDIA. I'm gonna just frame a bit how we think about AI and engineering, how we segment the different types of AI systems that we see emerging along the product development process, where SimScale plays today, sort of what's our work and what's our perspective. And I'll sort of put this a bit out there, and then I'm looking forward to hear Ian's point of view. NVIDIA is obviously a key player in the space. see his broader market perspective on AI adoption and engineering. Martin would have added a customer perspective on this, who's unable to join, unfortunately. And in the last 20 minutes, we're going to go into some real use cases. We're going to show some examples. We're going to do some real engineering work together, at least, what you can do within 60 minutes. And so hopefully it's not just slideware, but actually a sort of a concrete starting point that inspires you to take action and get ideas on how to get started. I'm not even sure if these days we need to motivate the why people care about AI, because frankly, like we a year ago or 1.5 years ago, like we actually needed to motivate a lot of engineering leaders. Hey, you should look at this. At this point, probably everybody is already. We're seeing so many initiatives. We're seeing so much drive and so much curiosity, which is awesome. But for what it's worth, if somebody isn't motivated yet, there's like every day there's now new benchmarks being published. This is one from Epoch AI, which I liked, which shows the progress and maybe a prediction on how good AI systems and software engineering are today. You can see this on the left, right? And where they might go. And again, everybody in software engineering, including ourselves here, has seen how capable AI already is today at writing good code. Again, we can see here the green part talks about fixing bugs and unit tests, or more like mundane work, but really already with more significant AI, sort of software engineering tasks, the AI system become better. And so the question is like, when will it do really fundamental software engineering work? This is a hypothetical prediction, so we don't, we're not in the business of predicting this, but it's more like it shows how strong the adoption in software engineering already is. And then with fast followers around math, with fast followers in biology. So we can see AI systems, frontier AI models emerge that can do out of the box work on some fairly fundamental scientific problems. And so that brings us back to the question, sort of, where is it in AI? Why am I still sitting down and drafting CAD? Why I'm still sitting down and sort of setting up a simulation, interpreting results? So where is that for engineering? And we're not the only person asking ourselves that. So in fact, like a lot of engineering leaders ask themselves this question. And so maybe as a small side note, we ran a survey. We also presented it together with engineering.com a couple of weeks ago. We ran a survey, we commissioned a survey among 300 engineering leaders across design and simulation on their adoption of AI. And I don't want to go into the details here, but the gist of it is there's a full report on our website. You can download it. But the gist of it is that that unlike roughly a year or 1.5 ago, everybody is extremely curious and expects huge productivity gains from AI in engineering, which again was not the case a year or 18 months ago, where there was a lot of skepticism still. But the problem and maybe the opportunity is that very few are seeing those gains already. We can see here what we typically say is like, less than 10% have mature AI programs in their engineering workflows today. 40% are POCing or testing. 50% haven't even started anything serious. And of course, again, we're here. I mean, the reason why we're doing so much work on SimScale on AI is the fact that a stack that is built for data management and process management and has the latest GPUs makes it easier to leverage AI, which we're going to see later. But hopefully, again, this bit busy slide here conveys the fact that many engineering leaders are actually actively exploring it, but few have seen it. Again, the reason for this webinar, because we've seen many just looking around, educating themselves, trying to find direction, and hopefully we can spark some inspiration with this today. So the question is, again, back to the question of why haven't we seen a big frontier model just do out-of-the-box core engineering work yet? And the challenge continues to be the big AI systems that we use for knowledge work today have been trained on large amounts of texts, have been trained on large amount of publicly available data, which is typically structured, which is typically open source. And there's no equivalent for such a data set in engineering. Engineering data is typically proprietary. You don't have access to it. And even if you have access to it, we can see the V model on the left. It's multimodal from systems model, from 3D, from 3D models over to hardware sketches, yada, yada, yada. So lots and lots of complexities in here that is not easy to use with the methodologies the large frontier AI models have been trained on. And so that's sort of where SimScale comes into play. We're working on sort of how can AI enter engineering. We're going to show it in a second. But at the end, we've been fortunate enough over the last couple of years to work with thousands of engineering organizations at this point on their adoption of a more aggressive adoption of digital engineering by means of AI, by means of broader deploy of simulation. And so here's a couple of stats about us. But where I actually wanted to go with this is the fact now, okay, we've heard, look, the frontier AI models can't do out-of-the-box engineering work. So what does this mean? Does it mean like I can't use AI in engineering? And quite the opposite. It's already in production today. Many organizations are already using it in production today, but it looks mildly different. And what we see here is a bit of like a simplified process chart of the product development process. Again, it's not in V-shaped. It's hard to put on a slide this way, but it's linear. And everybody, again, that is involved in a real engineering workflow knows that this isn't this linear. In the real world, you lose time in the iterations, right? Each time you identify a DFM problem and you need to go back to the drawing board and make a change. If a requirement changes upstream, that trickles down, yada, yada, yada. So this is where you lose all of the time. And what we see, why it's such an exciting time from our point of view in engineering, is the fact that we see the first AI systems in each of those parts of the product development process emerge. So we're seeing super interesting work done by companies in system simulation, in drawings automation, drawings review, DFM review. We see the first steps at more autonomous CAD editing, text to CAD, like many different flavors. And so each of those systems addresses one step in the product development process to accelerate, potentially even automate that loop. And the part now where SimScale, where we do our work, is we've built 2 AI systems that have the aim to drop the time it takes from the creation of a design to the evaluation, if the functional evaluation, the simulation of it, to drop that entire time to seconds instead of what is today sometimes hours, days, sometimes even weeks. The 2 systems, we'll call them engineering and physics AI. We're going to see them in action in a second. But the reason why we're showing this like a bit big picture perspective here is in the second half of this webinar, we're going to show how engineering AI functions, and we show concrete, we show a simulation agent, how it runs simulation workflows autonomously. And in physics AI, how simulation results can be predicted in real time by inference, by a neural net inference instead of a partial differential equation solve. But of course, the AI strategy is broader than only that part. And so depending on where your organization today has its priorities, that might be a good starting point. Maybe it's somewhere else. So we're going to close the entire session with a broader look on how customers today start defining full workflows where that is automated by AI. And so that's a bit the plan for later. Just before I hand over to Ian, we're going to see engineering AI in action first. Later, we're going to show, we're going to do a bit of work on a cold plate that we can see here on the left. We're going to have an agent help us do some work on cold plate design. We're going to then see real-time predictions of results of such a cold plate design, and then we're going to string these things together and say, like, how, with these new capabilities, if we really have AI entering the engineering workflow, sort of how could the engineering workflow of the future look like? That's something we're going to then dig in. So those are the 3, hopefully tangible, concrete, scaling AI and engineering, like a blueprint that might be relevant for your organization as well. Now I actually want to hand it over to Ian to get a bit the market perspective, and I thought, like, what better way to quickly explain sort of why Ian is here and why NVIDIA, because we've been working with NVIDIA now for a number of years on all sorts of parts of the stack, and what we can see it is a SimScale. We're going to see it later in action. And the stack behind it comes with a lot of, we do all of sorts of user data process, HPC management, auto provisioning, yada, yada, yada. Then we have the AI systems built on top of it. We have, lots of solvers, work with third-party solvers, and then the delivery of it. And the interesting thing is, also why I'm excited that Ian is here, is the fact that we're using NVIDIA technology. We've been working with NVIDIA on many parts here. Just to give a sense, we have GPU native solvers running in production, where the entire compute happens on GPU, some GPU acceleration of CPU-based solvers. There's an Omniverse integration for visualization, where NVIDIA technology is behind it. Of course, automatic provisioning of GPUs for training, for solving, for inference. On the visualization stack, there's some NVIDIA technology, and then in the physics AI system, there are actually components also from NVIDIA, model architectures from NVIDIA. So we're excited to partner with them, excited for them to join us here today. And at this point, I guess, Ian, I'd love to sort of hear your perspective on sort of how you are seeing AI and engineering being adopted, more like from a broader market perspective, to give the audience here the really like broad perspective of what you're seeing.
Yeah, thanks, David, for the introduction. Yeah, I'll try and talk a little bit about where I think we are, our thought processes and where AI can really help in the kind of computer-aided engineering processes. So I'll talk a little bit about that, and then like what NVIDIA is doing to enable it, and then just a little bit of background on some of the underlying platforms that help enable this. So generally, I always like to start with this slide because I think it kind of explains what NVIDIA is really, and what NVIDIA is a platform company. So we build a compute platform that developers such as SimScale can then kind of build these really cool tools that you'll see later during the demo. So I mean, people obviously think about the hardware at the bottom there of the platform, the chips themselves, but then we spend a lot of time putting those chips together into kind of rack scale systems to tackle some of the kind of hardest problems there are in CAE and AI by creating these large scalable racks scale systems. Then, of course, on top of all of that is the software, kind of the secret sauce, I guess, to NVIDIA, and that starts with the drivers, and then some of our libraries and some of the application frameworks that we actually also work with SimScale on, right? Like you already saw the integration of some of the AI architectures that we've kind of helped develop. But the key thing is really we build this platform to make it easy for developers to build some really cool, exciting tools. So onto this slide, and I think this slide for me really is the key one in my whole presentation, to be honest, because I think this really talks about, really where we see simulation going in the next few years. So, I mean, back many years ago, right, we were just doing physical testing, right, and maybe if we were lucky, if we just take a wind tunnel, we could do a couple of designs a week maybe. But then obviously we moved over to using more simulation, and we could, by using simulation and CFD and FEA, we could start to do even more different designs in a day potentially, rather than a week. So obviously that saved us time and money, so everybody was happy. But then one of the biggest changes is obviously accelerated computing, so running some of these tools on GPUs, and that's exactly what we've done. And now we can actually run these simulations potentially 10x 20x faster, which is again more designs can be examined. Hopefully you come out of it with a better design. But one of the biggest changes that's come after that is it using AI to actually help give us predictions, particularly early in the design phase, and then potentially to infer an AI model can take less than a second. So as you can imagine, the amount of designs that you can actually examine in that time is huge. And I think this is really important because I think in the past people have struggled to do things like design space exploration for complex simulations, right? Because it just takes too long, even with accelerated computing, right? So some of these approaches that will allow us to just examine the design space, much more broadly. But one of the cool things about accelerated computing, in some ways, for me, accelerated computing really enables the AI part, right? The combination of having a GPU solver to actually generate high quality training data for your AI training really makes it, I think, a lot more feasible to actually be able to train these models in a reasonable amount of time in the fidelity that you need. And one thing I would say, though, is that's not to say that I feel that these approaches are going to replace your traditional CAE. I think it's complementary to it, in the same way that CAE never replaced physical testing, right? We still have physical testing for the final validation, and then you still have, your traditional CAE to do the training and do your kind of more final validation cases, maybe when you've kind of looked around the design space using your AI surrogate. So it's not to say one will replace the other, but each one will become more complementary. And I'll talk a little bit about this more later, but the other thing I'd say is with AI, it's not like a CAE or AI approach. There's so many ways that it can kind of complement, and there's different pieces of AI that can help. So for example, it can help initialize a solution. For example, if you're going to run a CFD solution, rather than just guessing a flow field, then you can potentially use your AI surrogate to give you that initial flow field, and then still use your physics-based solver to get your final result. So they're places where it can really complement each other. And David touched on this as well. The other area, of course, is just some of the more mundane parts of the CAE process, right? Like there's a lot of setup, meshing, things like that should be ripe for more agentic workflows to kind of help some of those kind of duller parts of CAE setup. So I'm super excited about that as well. Okay, I'll move on to the next slide here. So how does NVIDIA do this? Like, what do we do that hopefully makes these things possible? Well, obviously, we provide a whole range of underlying technologies. And this can be things like, I won't go through all of these, but things like CUDA, obviously the programming language to actually make things work on a GPU is, as you can imagine, fairly key for both the, what I'd call traditional AI, plus accelerating your kind of traditional CAE solvers like CFD and FEA. The other one I'll talk a little bit about is probably is Physics NeMo, which is our kind of toolkit for creating these surrogate models that we'll see later on in the demo, right? And so, this contains a whole range of different architectures and underlying pipelines to hopefully make that easy to kind of implement into a program. And then lastly, Omniverse, which gives us this ability to visualize in a photorealistic way our simulations, because sometimes we want to create realistic digital twins of what we're doing, and the Omniverse APIs can really allow developers to create that. And another big part of what we do is, as well as CUDA, then there's a whole range of different libraries that sit on top of it for a whole range of different things. So Physics NeMo I've just spoken about, for example, the ability to create our physics-based surrogate models. A key one obviously is cuDNN, the first one you see there, which is obviously a way to accelerate deep neural networks. So pretty much all AI somewhere probably uses cuDNN to enable that to run quickly on GPUs. I won't go through all of these, but you can see there's a whole range of different underlying libraries that we offer. And a lot of them also to accelerate basic math functions that you might need to run as well. Like, for a CFD solver, AMGX is pretty common. For a structural solver, QDSS, direct sparse solvers are pretty common. So we need to kind of be able to run those on GPU in an efficient way. And so hopefully by having this kind of base layer available, it kind of accelerates the kind of rollout of being able to use these tools for everywhere. And that's exactly what SimScale have done, is to leverage some of these technologies into their platform. So it's easy for you guys to kind of leverage AI and accelerate computing. Okay, next slide. So I wanted to talk a little bit about the Physics NeMo side, because this is really where we've spent a lot of time recently developing these underlying models, both us and NVIDIA research, to start to enable different AI architectures to cover some of the different simulation use cases that you might want to simulate. So you can see a whole range of them here. I mean, CFD obviously is probably the main one you've seen. Interestingly, there's a whole range of different physics that we've simulated. So, we hope to see the use of these AI surrogate models spread from not just CFD, but a whole range of physical simulations. So I thought this was an interesting slide because, it kind of follows on a little bit from that first slide I showed, where we're kind of really talking about where we think AI can help the CA workflows. So it's not on here, but obviously the meshing and the geometry, I think there's a lot of potential here and to use agentic workflows to speed up some of those manual kind of repetitive tasks I spoke about. When it comes to the actual simulations itself, obviously, we can potentially use AI models as a turbulence model, or for a wall model, or for a collision model. So, some of those kind of add-on models that you use in simulation that might be slow, you could maybe use a surrogate model for those instead. Again, I spoke about using AI to initialize your solvers is a great way to leverage AI, and again, you still have the full accuracy of your final traditional solver. Then obviously further along the line, like I said, using AI as a surrogate model for your design and optimization cases that maybe before took far too long, or you were limited by the number of parameters that you could have in your design space exploration. So by leveraging these AI surrogates allows you to expand that much more. So particularly as most of you are probably designing pretty complex products with a lot of different constraints, then that really, I think, opens the door to having a much larger design space that you can explore by leveraging these surrogates. And ultimately, you can also mix and match things, right? Like, you know, I think the best engineers I know, right, their skill is being able to pick the right tool for the right problem. So potentially, you know, maybe there's some part of your workflow where the physics really are well understood, and you know, for that part of the design space exploration, you leverage your you know, your surrogate model, but maybe there's other parts that you know are less well understood, and maybe you add a more of a physics-based model there, or a traditional solver. So there's no, you know, it doesn't have to be an or, it can be an and as well, the way you combine these models and these techniques. And that's exactly what kind of SimScale have done by leveraging some of our different tools and architectures. You know, we've talked about Omniverse for the visualization. We've talked about using Physics Nemo as the underlying frameworks to generate these AI surrogate models, and then we, you know, combining that all together to make a really nice kind of tool where you can take it all the way through the workflow from you know, generating data in the traditional CA tools to training to actually leveraging those surrogates all in one place. Okay, I'll quickly flick through this just to quickly talk about some of the hardware and things like that we offer. I think most of you are familiar with it, but you know, every release of hardware, we're trying to obviously expand the use cases and things that people can do. So you know, we've had the range of GPUs. This is H200, but one of the things I want to point you to, because I think it's kind of interesting for CAE, is down here, this little table which shows the different generations of previous GPUs. So A100, Ampere, Hopper, H100, H200. And what you can really see is the amount of GPU memory going up, and on B200 it's up to like 190 gigs of GPU memory, and the memory bandwidth going up as well. And then these two things really, you know, predict how big a model you can run on GPU for accelerated computing, and also how fast it is. The memory bandwidth, often a lot of models are limited by the memory bandwidth. So every release, these things go up, which enables even greater performance. I'm just going to skip over this slide just for time. And also, you know, to run some of these things, it doesn't necessarily have to be the highest end GPUs. You know, we do have a range of really cool, what we call the RTX Pro series, which, you know, offers a lot of the same capability, but in a much more price performant form factor. So, you know, there's a whole range of different options that can help you, no matter, you know, what kind of resources you have access to. And again, we obviously keep iterating year on year and adding more capability to the platform. So Blackwell is the current generation of GPUs today, and then Rubin is coming, and then, you know, each year another generation of GPUs keeps coming. So every year the performance increases quite significantly. So I'll just finish with this slide. Really, again, I come back to this slide just because I think it's really cool, and I think it really tells a story of where I think we're going with AI and accelerated computing. And the one thing I would say is, it's worth starting to explore these areas, right? Like, hopefully, you know, most people in here are using simulation today, but, you know, can you speed up the simulations you do today by leveraging accelerated compute, and then start to use all of that good data that you're generating to actually create some surrogates, so you can actually start to explore the design space a bit more. So I think trying to move up this cycle is definitely what I'm encouraging people to do, and I'm seeing more and more people in industry actually, you know, start to do this in day-to-day production. You know, this isn't just a research activity anymore. We've got, you know, a lot of customers today actually leveraging this day in, day out. So with that, I'll thank you for listening to my slides, and then I'll hand it back to David so he can actually show you a little bit more hands-on actually these tools in action. So yeah, over to you, David.
Thanks a lot, Ian. Very interesting. Can you quickly do me a favor and confirm that I'm now driving slides? I'm hearing Abby send screen share is good. So Abby, I'm allowed to continue like this. Does that work? Good. Okay, I'm seeing yes. Good. Thanks a lot, Ian. Now, just 20 minutes on sort of getting a bit of our hands dirty on putting some of this into practice. And I'm going to do two things. I'm just going to show quickly engineering AI in action. I'll show a physics AI example in action. And then in the step 3, we're going to put them a bit together on what becomes possible when those systems act together. And before we jump into the systems of why two systems, why do they have this name? And we'd like to show, this little example today. We're using a small example of this cold plate. So, we have some sort of power electronics. This is an automotive cold plate, so the batteries sit on there. But you can imagine any type of, where you need to dissipate heat. And again, like this entire story, we could tell it. Sometimes we do demos with pumps, sometimes we do demos with assemblies, steel structure. It doesn't matter. Wherever designs are being generated, there's typically the phenomena that you have a design somewhere being generated. In this case, maybe an automotive supplier, responds to an RFQ, or an automotive supplier works on an NPD project, or an OEM works on an NPD project. Doesn't matter. Just the phenomena of the design has been generated, and it is a certain amount of time it takes for this design to be evaluated. And to some extent, like this is the rate limiting factor of the pace of innovation. So how fast can an engineering organization go from design generated to design evaluated? That's the incremental, the atomic unit of progress at how fast you can move into a design space. We can see on the right, again, hopefully everybody has now sort of a, you might not be in the design of cold plates, but in this case, we have a liquid, in this case, water coming through. And we have the engineering task here is like on the one side, we want to reduce pressure drop as much as possible to have the pump needed, dimension as low as possible. But on the other side, we need to dissipate sufficient heat. It needs to be sufficiently conform. You get the whole point. So it's a bit of an example design challenge. And so if we unpack now in how most organizations, how this wait time is composed, it's actually two separate parts. One is, and again, that's what Ian alluded to, is we call it the simulation cycle team. There's really sort of the simulation engineer presses on solve, or start simulation. The simulation goes off, starts running. And there's a certain amount of compute time that goes into it. And depending on the physics at hand, depending on the problem, depending on the model size, this actually might be sizable, right? And so this might be a real bottleneck. We heard from Ian, like optimization, but also we have customers that have simulations that actually run for weeks. And so that can be a real bottleneck. But it's not the only one, right? Probably everybody that does real engineering work that is in the room here knows that there's more than that. The time it takes an organization between design generated to design evaluated is not just solve time, but it's actually, we call it simulation lead time. So all the wait times, the handoff times that go into this design actually being picked up. And again, I guess you know this better than me, but like as in like a design for simulation, like a request for simulation, request for analysis, request for engineering time is filed, and then it takes some time until this bubbles up in the simulation team. There might be a meeting, there might be a clarification. Then again, all the work the simulation engineer Ian again talked about it around CAD preparation, mesh generation, etc. So the full time it takes for design from generation to evaluation is really those two parts. And that's why we're building, or we've built two AI systems to address those. And the first one that I'm going to show you is specifically for simulation, the engineering AI system, that's an AI system we've woven into SimScale, where like a reasoning model is able to perceive, to monitor the context, the simulation context as a simulation is being set up with SimScale, can interpret it, can perceive it, can make decisions about it, can autonomously run simulation workflows, again, based on instructions and guardrails an engineering team has given to it. So to a large extent, we see this type of technology entering different parts of engineering workflows. And again, today already in legal tech or in marketing tech or in sales tech, this is already much further advanced because the contexts are typically purely text-based. In engineering, it's more complicated. So we need to do work around CAD and 3D modeling and simulation setups and physics and whatnot. But we believe the ultimate workflow will be very similar, where again, these days, everybody calls it agents, but where an AI system is able to autonomously run engineering workflows, again, based on certain guardrails. We're going to see it in action in a second. And the second part, what we've heard Ian alluding to is physics AI, so an AI system that based on past simulation results can infer future simulation results. And that without any significant compute, and so you get to instant predictions of simulation results. And those two systems really are to some extent symbiotic, because one part automates the manual, the other one accelerates the computational. And depending on the workflow, depending on the organizational context, one system is more important than the other. But we think like both are ultimately needed to drop a simulation lead time to seconds, and really, going back to SimScale's mission, help engineering teams making thousands of engineering decisions in seconds. So now let's take a look how this concretely looks like. We're going to stay a bit with the example of this cold plate, and I'll show we are kind of okay on time. So I'll also do like a small live demo of both systems, but just to convey the the fundamental principles of how this works. What we're looking at here is like a screenshot of the SimScale UI. And you can see this is sort of the data management panel, and where all of this starts, where you manage projects, where you manage your users, where you manage data processes, templates, etc. And among others, there's on the left the ability to manage physics AI models, and then engineering AI agents for your organizations. And under engineering AI agents, what it allows you to do is define an engineering AI agent and give it instructions and give it reference data on how certain simulation workflows shall be run. And we're going to see it in action in a second, but I think the right mental model to think about it is every simulation team we work with has already, of course, some sort of automation in place, Python scripts, sometimes an SPDM system, sometimes maybe some internal tools they've deployed, etc. But typically, those systems rely on hard-coded macros, hard-coded Python workflows, etc. And they do their job. The weakness of it is that they are very fragile to input variations. So what if the supplied CAD varies a bit? What is like the input conditions of the user vary a bit, or deviate a bit from the standard? What if the solver behaves suddenly in an unexpected way? Yada yada yada. Each of those points typically leads to the workflow exiting, which makes it a fragile process to automate this way. And so with an agentic approach to automate it, where you have a reasoning model basically monitoring the simulation context as it evolves, you have the ability for the reasoning model to actually, based on instructions and based on guardrails, to react and make decisions. Again, as an example, if the agent, the AI agent running simulation workflows, finds a CAD model where certain topological labels are missing that you actually expect in this type of simulation workflows, what shall the agent do? Shall it continue or not? If there's a mesh quality warning, should the agent ignore or should it continue? To a large extent, instructions you would also give a junior simulation engineer can be given to a reasoning model to then run autonomously simulation workflows. And again, there's more here to uncover. We didn't go into details of how to give instructions, how to give good instructions, how to give guardrails, so we'll not go too much into it. But an important point that I want to make is like that this is something that doesn't require a large IT project, that does not sort of, like a collection of, terabytes of data to start something, etc. This is, given the right stack, these types of methodologies of agentic AI become easy to do. And so we'll just checking time. I think we should be okay with a quick hop over. And can I once again ask if we're seeing the SimScale product now? Yes, yeah. So you can see a 3D model of a battery pack. So we'll see an AI agent in a second also that works on the cold plate. But here's a small different example. That's a battery pack, and like a valid question now could be sort of like design engineers made some changes to it, and we're concerned with the harmonic response of this battery pack to vibrations. If I need different rubber mounts, if my if that's taken care of. And so, of course, like with SimScale, you can now run the simulation from scratch. So you can create a simulation, you can actually import template simulations, etc. So this can be done, but with a dedicated agent for it available, what can be done as well is to actually go in and ask the AI agent to do this work for me. So now this agent has been instructed how we typically run these kinds of harmonic response analysis, what our standard materials are, for certain parts that it recognizes in the CAD model, etc. And so what I can now go ahead and do is what is the harmonic response of this design to our standard load case, given our standard materials and CAD labels, fully automatic, please. Again, I haven't checked now the detailed instructions of this agent, so we'll see now what this agent does. But hopefully that you see the principle of this implementation of our AI agent, where now this agent goes off and sort of sees the CAD model, understands the topology, analyzes the topology, has been given instructions before, and so I have my hands off here on the side, and now it analyzes. The user asks for a harmonic response analysis. I'm seeing certain examples that have been run before like this. So I'm using those setups to actually apply to this one. And then it tries to reason through, do I find enough information in CAD labels to assign the materials? If not, do I have instructions on how to identify certain parts based on our, data that we have in the PLM, et cetera? And so what we can now see it doing is going through sort of the different parts of this model, setting up material definitions, again, based on what my engineering team has given it in terms of instructions. So we're done with material assignments. And as the next step, it would then go ahead and sort of, in this case, a harmonic response requires some boundary conditions. So it fixes some supports, it finds some labeling, identifies, yada, yada, yada. This is, again, a bit of a very fast, quick demo here, because at the end, of course, every engineering organization has their own workflows. So this is a bit of a prepared demo because we're looking at sort of an example we understand. So for a real-world deploy, you would want your simulation agent to be instructed by your team, to given examples, etc. But hopefully, you get a sense for on the right stack, on a stack that's built for AI integrated. Of course, we want to ignore this. This is a demo. Yes, of course. Go for it. And in this case, sort of the agent asked, look, I can see some warnings. Do I want to go? No. But in this case, we just run it. And so the agent now kicked off the simulation. And so we have this sort of this autonomously, this agentically automated simulation workflow completed. The same, I had the video, I think, over in the presentation. So let's hop over. Again, the same for, it's just 1 minute video. So just to see it again here. This is now the version not live for the cold plate that we looked at. So we can see we have actually a dedicated battery plate CHT agent. We ask it to do what? Evaluate the thermal performance of this cold plate. Again, using our standard approach, the standard approach and the standard load case, the standard flow rates, the standard heat transfer, et cetera, has been defined in the agent instructions. And now the agent goes off. You can see it on the left. It understood, okay, this is a conjugate heat transfer problem. So it uses the appropriate analysis type, runs contact detection, assigns materials, assigns appropriate materials based on what my engineering team typically uses for cold plate designs. Again, could be a different liquid. Assigns materials, goes through boundary conditions. Again, similar to what we've seen before. But with the element that this is not a script that is executed, but actually a reasoning model being able to think through and help autonomously and intelligently automate simulation workflows, and thereby broadening the corridor, if you will, of simulation workflows that can be automated. Our gentleman here is almost finished. We will share in a second here. What I want to share at the end of, in about 10 minutes after we took a quick look at physics AI is what I want to then sort of at the end is like what we're looking at here is the agent integrated in SimScale. For many customer deploys and customer collaborations, the agent is actually not deployed inside SimScale, so they have agentic workflows that work headless. They of course work together with SimScale, and they use SimScale in the backend, but the agent is interfaced in a different way. I'm going to show it at the end of the presentation quickly, but just to get an impression. But hopefully we'll get sort of now a sense and sort of a concrete feeling of an AI agent sitting next to us running simulation workflows for us, right? How is that? Abby, are we still okay here with screen sharing? Does that still work? Excellent. Okay. Then just 5 minutes before I wrap this up. So this was, okay, we have one part, an AI system automating the manual work around simulation workflow. And then now the next one was about how can we cut down solve times? And I think this is something that has been, I think, seen more in the industry already. And so I'll go quickly over it. So, we have now this design And so my organization happens now to generate many of those simulations. We can see here, can you see the different slot designs? So we're looking at varying number of segments, varying number of slots. So all of these are different designs, and we're looking at the pressure field. And so as an engineering team in this case would use SimScale and sort of amasses more and more data, that data can then be used with, again, a physics AI system integrated into SimScale to train physics AI models to predict physics results with inference. And I guess we're seeing different types and different kinds of these projects. Some are truly where just by having many design engineers and many simulation engineers using SimScale, they just amass data automatically that then can be used to train these models. Sometimes it's for a dedicated project where they run a design of experiments to generate the data and then train a physics AI model. Sometimes it's for operations use cases. So there's different setups in which this is happening. But at the end of the day, you have this data, and then with the integrated physics AI capabilities inside SimScale, you can now train a physics AI model. And we're going to quickly see that. And I'm getting warnings here that we need to wrap up. I promise 4 minutes. I'll be finished at 50. So let's take a quick look. Maybe then we'll cut out the live demo of a physics AI model. But just to get a sense for how now this looks like, what we're looking at is 2 different designs. You can see the different slots here, right? So again, we've ran some simulations, and we now have a set of simulations that we now want to use to train actually a physics AI model. And what we're looking at here now is we are going in and are defining a new physics AI model. We've defined it inside SimScale. We're choosing the data based on which we want to run. In this case, a very small sample set. We're choosing the simulation runs. We're giving it a name, and are about to send off the training workflow for this simulation. So in this case, what we can see is now the sort of a cold plate V1 model AI training has been started, physics AI training. We can see over time the progress is being tracked. So we can see the training loss, validation loss, as this physics AI model is being trained on the data, to eventually, once it's finished, be able to release it within SimScale and deploy it broadly into the organization. And what time doesn't permit maybe at this point is that the way then these physics AI models is being used is exactly directly next to the actual partial differential equation solver. So what we can see here at the top is, you can see on the left the normal finite volume, the normal simulation has been deployed, but because the physics AI model is being deployed in the exact same environment, you basically don't have to choose between one or the other because they sit right next to each other. So you literally can have a simulation setup built up, and then if you have an appropriate physics AI model for it, actually evaluate it via a physics AI model. Or if you do not have enough coverage for that, you deploy you simulate a normal with a normal solver. And then of course, maybe the last example here is what then people do with this is suddenly an evaluation becomes instant. And so it doesn't require any serious compute. It becomes instant. And so we can then, obviously, we have the door open for optimization, design space exploration, operations use cases, real-time responses, because you're suddenly in this, from geometry to evaluation, you're suddenly in real time. And we can see here now on the right one, like the good old, pressure drop via heat dissipation can then be done in minutes. So we can evaluate hundreds of design points in minutes, all simultaneously, and open the door to just like in a much more aggressive way explore design spaces. And then with that, I want to wrap this up. The last point that I wanted to make, because hopefully now you've seen like a concrete example of an agentic workflow for automating simulation workflows. You've seen a concrete example of physics AI, how it's done. I hope the videos and the small live demos showed that this is in production today. You can go in, you can do it yourself. And now the third point is what we're excited about is now how customers are putting this to work is, of course, like we've shown it sort of with the integrated capabilities, but then also the ability to actually put these workflows into different contexts. So for example, here, we see like small visuals of, because you can suddenly now prompt simulation workflows, you can, put your interface somewhere else. And this could be like a communications platform. In this case, we can see a little mock-up of Microsoft Teams or a Slack channel from which you can send off simulation workflows. But it could also be, depending, you might have a project management tool, Jira, or some, issue tracking system where a a team where where your agent actually listens to the project management tool and then goes off and does work, or to a shared inbox. So suddenly, because you now have like this flexible way of automating simulation workflows, new possibilities arise. And so, simulation automation is one use case, design space exploration is another one. Design optimization is a third one, and then a last one, just in the interest of time, flipping through this, compliance analysis, code compliance simulations, where you have certain guidelines that you need to adhere to. That's something that's then can be done in this context as well. Really bringing out like this making way more simulations, way more design decisions in a broader context in the engineering team. With that, hopefully, sort of we gave some inspiration today, and I guess maybe the few mini points to take home are some of this. I think most of them I made clear. I think we heard in the early days that many customers are stuck in pilots, and so I think there's if we think about real workflows, that's the path to go. The second one is maybe sounds obvious, but oftentimes people try to start, pointing AI to the most challenging workflow, which is probably not the best way to start. Better the boring one. The physics AI role is in accelerating simulation. We've heard it before, not replacing it. That's probably the one that we're excited about. At this point, AI in engineering is not an IT project anymore. It's really sort of more like how willing is the engineering team to actually explore these methods. And then I guess last but not least, hopefully this is the one where we sparked some interest, that some customers tell us, or some engineering teams we talk to, is sort of, they are in the early days, they're trying to formulate a strategy, but at the end, we're all engineers and we like to just get our hands on something, try it out, prove its value. And we think at this point the technology, the AI systems are so mature that this is possible today, that it doesn't have to be a big IT project, that you can start on a smaller scale, just exploring new things. And if there's something you want to talk about, we're of course happy to. We have the material. You have the materials available. If we want to have a conversation about that, we're happy to have that one. I guess with mild overdue, I think at this point I'm done, and would hand it back for the wrap up to the engineering.com team.
Thanks so much, David and Ian. And wow, that was one heck of a presentation, and caused a lot of engagement. We have tons of questions. We're never going to get through all of them. So I'll pick a couple and then we'll go from there. One of the first ones is maybe a good one for David. How do we minimize the hallucinations of the reasoning model in AI? Is this still a big problem for us in engineering?
I mean, clearly so yes, I mean, this is a problem. It's not like that, I think like any discipline that right now puts AI into real world workflows is something that they deal with. And I think there's a lot of fundamental research going on that will reduce these things. But then also, I think the important bit here is to keep in mind is at the end of the day, everything the agent does is fully auditable and inspectable. I might have not made this 100% clear on this product development slide. So the way to think about it is you send off an AI agent, again, worst case, there is an hallucination in there, sort of a bad decision being made. Everything the agent has done is fully inspectable because the entire state of the entire simulation workflow is managed on SimScale, right? So you can go in, what simulations did the agent choose, how are the results, how are they computed, everything is auditable. And so at any point in time, you can control, you can give guardrails in the agent definition, when to involve a human, when not. So I think there's lots of work fundamentally being done on reducing those, but then also the way at least we integrated this is with the conviction that an agent will make mistakes, and the same as a junior engineer makes mistakes. And so SimScale built a lot of technology on, for example, facilitating safe collaboration between simulation experts and novices. And so there's real-time collaboration, there's reviews, there's central governance mechanisms, and they work surprisingly well for agents suddenly do simulation work as well. So that's a bit the quick answer to that. The reason why I don't want to go into sort of guardrails definitions and like how to instruct and how to set temperature values and whatnot. So there's many technicalities around that, but I think at a high level, that's how I would think about it.
Excellent. Ian, is there anything you'd like to add to that one, or?
No, I think David captured it pretty well. I mean, the only thing I would say is obviously, at this point, as the engineer, you still, I think, have that responsibility to check and make sure what you're doing makes sense. Same with any CAE tool, right? Even if you're running a CAE tool today, right? It's, generally you want to avoid blindingly taking those results and and using them. It's always best to use your own engineering intuition to make sure that the physical values of interest are actually make sense based about around what about the problem.
Excellent. And it's still, frankly, early days. I mean, I think this is something that's going to be reduced as we continue to go. So, there's a ton of questions here. We try to get you guys out at, 55 past the hour, give you 5 minutes extra to get yourself organized. So we're going to call it a day. And that's all the questions we have time for today. However, we will get these questions answered offline. Several of them are, I think, very well suited to offline question and answering. So we will get those to you. Feel free also to contact our presenters on your own. And this webinar will be shared with everybody so you can view it again at your convenience. I'd like to thank David and Ian and, Martin for wanting to be here, even though he was not, for taking the time to help us understand this, AI in the engineering process. And I'd like to thank everybody here for joining us today. I hope to see you tomorrow for our final webinar in Digital Transformation Week with our special guest, Brian Zakrzewski from Deloitte, who will help us understand how to set and manage expectations of what digital transformation can really do for your company. So until then, have a great day, and thanks for coming. Bye now.